Welcome back to differential equations. If you recall, a differential equation is simply an equation that involves a function and one or more of its derivatives, such as the first derivative or the second derivative, or both or higher order derivatives entirely. So we're going to start with a sort of generalized form of a particular differential equation. All right, this one right here that says dy dt equals ky. All right, and before we even go ahead in trying to solve this, we want to think about what this differential equation is actually saying. All right, so let's just take this piece right here, dy dt. All right, and of course we're assuming that we're working with some function y, right? So that we can get, y prime, y double prime, etc. All right, and based on the notation here, we would assume that y is a function of t. And the use of t here is deliberate, right? Because it will imply time in this context. So dy dt, what does that actually mean? Well, really, that means the derivative of function y with respect to t, right? So the rate of change of y over time. So let's write that in. The rate of change of y, whatever function y is, over time. And hopefully yours looks a little prettier than mine right now. Okay, so dy dt, the rate of change of function y over time, or you could even think of it as the rate of growth or decay of function y over time. Well, what does an equal sign tell us? An equal sign tells us is. That's pretty easy right there. Is. So the rate of change of y over time is, and then let's look at this piece here, k times y, right? So the rate of change of y over time is function y itself times some constant k. So really, the way that we would interpret that mathematically is to say that the rate of change of y over time is proportional to y, right? If something is a scalar multiple of another, those two quantities are proportional. So we're going to write proportional. And we're just going to make sure that that's actually an O. Okay, so the rate of change of quantity y over time is proportional to y itself. All right, and let's think about what that might mean. All right, in other words, the rate at which your function is changing depends on how much there currently is. And ultimately, if you were to rack your brain enough, you might be able to come up with the idea that this implies a percent change, right? For example, if you increase something by 5% each year, the amount that you add each year is going to be different based on how much you currently have from year to year. So that's what this really models. It models growth with a constant percent change. All right, so now let's actually get down to business. Let's solve this differential equation. Maybe remember our separation of variables a little bit because it's been a while, and we'll see where that gets us. Okay, so let's write down our differential equation. So we've got dy dt equals k times y. All right, so to separate the variables, of course, that means that we want all our y's on one side and all of our t's on the other, and we would prefer that dy's and dt's be in the numerator, right, so that we set up an integral correctly. And the k, well, it's a constant, so it really doesn't matter where it is. So the first thing I'm going to do is multiply both sides by dt. And then I'm going to divide both sides by y. I'm just going to leave the k on the right-hand side. So that gives us, dy over y equals k times dt. variables are separated, y's on one side, t's on the other, k is just a constant, so now I can go ahead and integrate both sides. So the integral of dy over y equals the integral of k dt, and hopefully that left-hand side is just screaming out to you, natural log of y. Okay, so let's come over here. And so that means that on the left we have the natural log of y equals, and then the integral of k dt will just be k times t. And then technically we have a constant of integration on both sides, but right, when we're solving a differential equation, we can just sort of lump them both into one giant super constant on one side. And so then if you remember, the goal of solving a differential equation is to find the function y such that this information over here holds true, right? So we need to solve for y. So we need to get it out of this natural log. And of course, the way to do that is to exponentiate both sides. So I will say e to the left-hand side equals e to the right-hand side. And just be careful that that plus c, remains up in the exponent. Okay? So, of course, e and natural log will cancel each other out, leaving us with y equals e to the kt plus c. And now we're just going to use a property of exponents sort of in reverse, right? We have a property of exponents that says that x to the a times x to the b is the same thing as x to the a plus b. And so we're just going to use that in reverse, that if we had added exponents, we must have been multiplying like bases. And that will let us write y equals e to the kt times e to the c. And then we say, oh, wait a minute, e is just a constant. So some constant raised to another constant, well, that is just a different constant itself. So ultimately, we can write y equals e to the kt times c, or more elegantly, y equals c e to the kt. Now, you can go through this process every time and solve this differential equation to arrive at this solution. Or you could just remember that anytime you have a situation in which the rate of growth is proportional to the amount present, that your solution is going to be of this format. All right, so let's put that here. All right, that if you are given a differential equation of the format, and again, it doesn't have to be dy, it could be dA, dt, or whatever, right? But anything that fits this format where the derivative with respect to time is proportional to the amount present, you can skip the actual process of separation of variables and know that the solution fits this format. Also, just a couple of little vocabulary pieces here. In this case, C is going to correspond with your initial condition, right? And by initial condition, of course, we mean the amount at time 0, right? And hopefully you can see that if t goes to 0, right, e to the 0 is 1, therefore y of 0 is c, right? And then k is called the constant of proportionality. And that'll usually just correspond with the percent growth or decay. But this is what you want to stick in your memory right here. Okay, and so now we get to the actual applications of this stuff. And here's the thing. If you can manage to recognize that you've got this type of growth scenario happening, these become less of a calculus problem and more of a pre-calculus problem. All right, so example 1. The rate of changes of y is proportional to y. Ooh, okay, so that should jump right out at us, right? This sentence right here should tell us that we are looking at something like this, right? That we have the rate of change of y, probably with respect to time, is proportional to y. And so here's the nice thing. We know that if that is a property of function y, if that differential equation holds true for y, the solution to that differential equation looks like this. And we can save ourselves the step of doing the integration, right? Why would we need to do the integration? Well, in the first sentence, the rate of change of y is proportional to y, right? But then it says when t equals 0, y equals 250. And when t equals 1, y equals 400, right? What is the value of y at t equals 4? All of this to say they're asking you about function y. They're not asking you about y prime or dy dt or the rate of change of y. So in order to answer these questions, we need function y, right? So luckily, we know that function y is of the form ce to the kt. All right, so now we just need to start using the information that they've given us. And we're going to start with this first piece. When t equals 0, y equals 250. All right, so let's plug that in. All right, so y is 250 when t equals 0. Right, notice we don't know what c and k are, but we're going to slowly start to figure it out. All right, so that gives us 250 equals c e to the 0, which means that 250 equals c. Oh, yay. All right, so we can add that into our formula, right? So far we have, right, y equals 250 e to the kt. Now we will need to figure out what k is in order to have a complete formula for y and answer the questions. Right, now notice we also have the second bit of information about what is going on when t equals 1. Right, when t equals 1, y equals 400. So we can set up y is 400 when, and now we know that c is 250, right? E to the k times 1. So that leaves us with, right, really 400 equals 250 times e to the k. And so then we just, this is a pre-calculus problem. Let's solve. So let's divide both sides by 250, and we will get 1.6 equals e to the k. And then it's log time. Natural log of 1.6 equals the natural log of e to the k, right? Which leaves us with the natural log of 1.6 equals k, right? And the natural log of 1.6 is 0.47. All right, so our complete formula is y equals 250 e to the 0.47, that's a 7, work with me here, t. All right, and so now we can actually answer the question that it's interested in. I'm going to have to go off the page a little bit, all right, because it wants to know what is the value of y at t equals 4. Well, actually, you know what? You can do that. You can plug in t equals 4, and I will just tell you that it should work out for you that y of 4 is about 1638.376, right? That's not the hard part. Great. Next. Okay, example 2. So for radioactive isotopes, the rate of decay is proportional to the amount present. All right, so I'm going to pause right there because you can read the rest of this, right? But this is what we're looking for right here. The rate of decay is proportional to the amount present. That tells us, right, that the rate of change of quantity y over time is proportional to the amount present. All right, and so from there, we can then jump right to the solution, which we know will have the format y equals CE to the KT, and save ourselves some time. All right, Now, it says in 1986, there was a little whoopsie at Chernobyl, a nuclear power plant in the Ukraine. All right, suppose 10 grams of plutonium were released. How long will it take for the 10 grams to decay to just 1 gram, given its half-life? Okay, so notice, this is how we know that we even need this statement in blue, right? They tell us about the rate of decay, and then they start asking us questions that relate to the amount, not the rate. So that would tell us, well, we need to solve this differential equation that they've given us, right? And again, you can always start from scratch, but if we just know that this differential equation goes to the solution in blue, you can save yourself some time. All right, and then if you know that much, it becomes a pre-calculus problem. So let's get going. All right, so we know that our solution is going to be of the format y equals CE to the KT. And so let's see what we can pluck out of here. All right, so it says, suppose 10 grams of a plutonium isotope were released. So that just gave us our initial amount. You could plug in, the fact that, oh, that means that at T equals 0, there were 10 grams, but I'm gonna kind of skip that step and just write what we can infer, which is that we're looking at this. So we've got that, great. All right, it also tells us, all right, that the half-life is 24,100 years. Now, hopefully you know what half-life is or you have a rough idea, right? But half-life tells you how long it takes for a quantity to be cut in half, right? So if the half-life is 24,100 years, right, that means that if we start with 10, right, and we don't know what K is, all right, but we do know that when 24,100 years have passed, we will have half of the amount that we started with. All right, and this will let us solve for the decay constant, K. All right, so if we solve this, we end up with 1/2 equals e to the 24,100 K. And now it's time for natural logs. All right, so the natural log of 1/2 equals the natural log of this entire right-hand side, and that's a comma. Okay, and then I'm gonna come over here. All right, and from there, the natural log of 1/2 is roughly negative 0.693. Natural log and E are basically going to cancel each other out. And then solving for K is very easy, right? We'll get that K is approximately negative 0.1234 zeros, I think. Which kind of makes sense because that should tell us that this thing is decaying very slowly. All right, and so this here lets us get a complete formula. Y equals 10e to the negative 0.0002876 t. All right, again, so, if you think that would imply, let's see, a 0.00286% decay each year. So this stuff decays very slowly. All right, so then to actually answer the question, all right, it says how long will it take for the 10 grams to decay to just 1 gram? All right, so that would imply that there is 1 gram remaining. And that is a 7. Okay, so then we're going to have, all right, we'll divide both sides by 10, and just to save myself a little bit of writing here, I'm going to say we'll divide both sides by 10 and then take the natural log. So we'll have the natural log of 1/10 equals the natural log of e to the all of this business. Okay, and then, so let's see, the natural log of a tenth is about negative, 2.30259. And then again, the natural log and e are going to cancel each other out effectively. That's a negative sign. All right, this just does not want to make sevens. All right, and so then when you divide both sides by that giant decimal, all right, you're going to get that t is approximately 80,000 years. And this is why a little nuclear whoopsie like the one at Chernobyl is such a problem. This stuff decays so slowly, it takes a very, very, very long time for the amount to reduce enough to the point where it's not dangerous anymore. Okay, next page. This now brings us to a different kind of exponential growth, but one that is oftentimes a lot more realistic, especially for population modeling. All right, so as it says here, exponential growth is unlimited, but in nature, that's not really reasonable, right? Because any given population, whether it's a population of deer or a bacteria or people, right, it's not just going to grow exponentially forever. And hopefully you could figure out why that might be the case, right? Eventually, its environment can no longer sustain such large numbers. And then, you know, based on limited resources, right, the population would start to die until it had decreased to a reasonable amount that its environment could sustain. All right, so anytime you have a population in an environment, right, where there is a carrying capacity, right, in other words, a maximum number that can be sustained, this is going to be more accurately modeled by what we call a logistics curve, all right, a logistic curve rather, all right, which means that after a certain point, the exponential growth is going to start to level out. And I encourage you to, at some point, when we create a logistic growth model or logistic growth equation, to put it in Desmos and graph it and see what it looks like. I believe I even had you graph a logistic curve for one of your problem sets. All right, so it's got that S shape, right? Kind of looks like, right, starts out, it increases rapidly, and then it levels off based on the carrying capacity. All right, so a logistic curve, all right, has a rate of growth that can be described by this differential equation. All right, so notice the first part looks the same, right? We've got this chunk right here, dy dt equals k times y, right? So the rate of growth is proportional to the amount present, but then there's this other little chunk times 1 minus y over L. So something to keep in mind, all right? Y is the amount, right? So it's proportional to the amount, all right? And in this case, L is a constant, all right? And L represents the carrying capacity, okay? So something interesting happens. This second little chunk that's attached to our typical, you know, exponential growth differential equation, all right, does something very interesting. All right, hopefully, all right, you can see, all right, that if we have the case where y is less than L, in other words, if your population is less than the carrying capacity, well, let's think about what is going to happen. All right, if y is less than L, if your population is less than your carrying capacity, well then, that means that this term is going to be less than 1. Therefore, 1 minus that will be positive, right? Therefore, dy dt is positive, right? So I'm going to write that down, right? And if dy dt is positive, that means that, right, your rate is positive, so your population will grow, Okay, so let me just take some of those markings away because I'm going to attempt to do this again. All right, so now let's see what happens if y is greater than L. All right, if the population is greater than the carrying capacity or exceeds the carrying capacity. All right, well, if y is greater than L, then this second term here is now greater than 1. So 1 minus that term will be negative, and that would create a situation where dy dt is less than 0. So your rate of growth is negative. In other words, right, your population is shrinking, not growing. And that makes sense, right? If your population is less than your carrying capacity, your population is going to continue to grow. If your population exceeds that carrying capacity, your population will shrink. All right, so that's what this differential equation is doing. And so you're going to want to be familiar with this. You should be able to recognize, all right, this situation here as logistic growth. Okay, and so now what we want to do, all right, similar to what we did for regular exponential growth, we want to solve this differential equation and then see what function y looks like. We want to see what its solution looks like, because here's the thing. Solving this differential equation is a little bit of a project, and you are definitely not going to want to do this every time. So if you can take the shortcut and just know that this differential equation has this formatted solution, you're going to save yourself a lot of time. But we have to derive it at least once, right? So let's get to it. All right, so coming on down here, here's what we're working with. We are working with dy dt equals ky, just like normal, but now we've just got this extra term that tells the function whether to grow or shrink. All right, so the first thing that we're going to do, of course, all right, is separate our variables. All right, so I am going to divide both sides by this entire quantity here. All right, and in that same step, just to make it not so bulky, I'm going to multiply both sides by dt, so that I will have dy over 1 minus y over L equals ky times dt. All right, and now I am almost separated. Okay, I just need to divide both sides by y over here, and I will have my variables completely separated. All of my y terms on the left and all of my t terms on the right. Again, k is just a constant, L is just a constant. All right, and L is a property of your particular population, so that would be given, or you would have enough information to find it. Okay, so let's divide both sides by y, and that will give us dy over basically y times this quantity, right? Equals k dt. Okay, and now here's the hard part, all right? Ultimately, we know that the next step, once our variables are separated, we know that we need to integrate both sides. And I'll say, okay, it's not hard, it's just a lot of work. All right, so I'm going to kind of give it to you, but hopefully you can start to think about what method would you use to integrate this. And the answer is partial fractions. Okay, so I'm just going to help you with the partial fractions decomposition. All right, and so ultimately, all right, what you would do is you would take apart this piece right here, right? You would look at 1 over y times the quantity, 1 minus y over L, right? And you would say, in fact, you know what? I think I'm going to do this in a different color, just to reiterate that we're just working on the partial fractions here, right? And you would say that that's going to be something over y plus something else over 1 minus y over L, okay? And then when you do this, right, you should find that a equals, all right, a equals 1, and you should find that b works out to be 1 over L. Okay, so let's go plug that in up here. All right, so here's what we have. All right, so we are integrating 1 over y plus 1 over L, right? That was b over, 1 minus y over L, and then that's dy. And then on the other side, we're going to have, right, equals the integral of k dt, which is easy. Okay, and then one way to actually make this even easier to integrate, all right, the first fraction is easy, right? 1 over y, that's not the issue. But this second term is a bit of a mess because of the complex fraction. All right, and so I'm just going to clear the denominator. All right, so I'm going to multiply, right, both numerator and denominator by L. Okay, so that will give me, this was supposed to be a plus sign here. Okay, so that will give me, right, well, L times 1 over L, that's 1. Then here, right, L times 1, that gives me L. And then L times y over L will give me y. And that's a lot better. Okay. So now I think we're in a place where we can actually integrate this. All right, so let's go ahead and do it. All right, when we integrate the left-hand side, well, 1 over y will go to the natural log of y. And then 1 over L minus y will actually go to negative, right, to account for chain rule. So it'll be minus the natural log of L minus y, right? And then on the other side, all right, we know what k dt is going to go to. That's going to go to kt. And then I'm just going to put one big plus c at the end there. Okay, so now here's the thing. Solving for y in this case is a bit of a pain in the neck, I'll be honest with you. All right, basically you have to use some log properties to bring these together, right, and say that this is the natural log of y over L minus y. Then we have to exponentiate both sides. So basically, right, do e to the left equals e to the right. I'm just going to do that like this because I'm running out of room. Okay, and then e and natural log effectively cancel one another out, and I am left with y over L minus y equals, and then on this part here, I'm going to use my reverse exponent property again and say that that is e to the kt times e to the c, so that I get y over L minus y equals c e to the kt, because again, e to some constant is just another constant itself. All right, now we're pretty close, all right, to solving for y. The rest of this is just a big algebra problem, and you know what? For your own benefit, I encourage you to do it, but at the end of the day, all right, you should be able to get it to this format with the powers of algebra. L over 1 over c e to the kt plus 1. And then up in the box up top, I'm going to show you how we more typically notate that. We give it as y equals L over 1 plus c e to the negative kt. And that's to just avoid complex fractions, okay? So again, I've skipped a lot of steps here. I encourage you to go through it yourself and verify that this is the actual solution to the above differential equation. All right, but truth be told, I'm just running out of room. All right, and so, yeah, I hate to tell you, that's going to be one of those things that you just want to know. All right, and so on the next page, we'll do an example, and you'll see how this all goes into, put into practice, rather. Okay, here we go. 40 elk are released into an animal sanctuary. After 5 years, the elk population is 104. The commission believes it can support no more than 4,000 elk. Okay, so right there, that to us indicates a carrying capacity, which we denote with L. Estimate the elk population after 15 years. All right, and so really, that item that I underlined there, that's kind of all you have to go on. All right, that tells you that we're looking at logistic growth anytime there's a carrying capacity. So we know, all right, that if there's a carrying capacity, its rate of growth can be described by this differential equation. And then hopefully we know that if we are working with that differential equation, all right, we know its solution. Its solution takes this format. And again, how do we know that we even need that? Well, it says estimate the elk population after 15 years. It's not asking us about rate of growth, it's asking us about the quantity, the actual population. So we would need to end up solving that differential equation. And based on our work on the previous page, I hope that you can see why being able to jump to the solution in blue is helpful. All right, so let's start. All right, let's see, 40 elk are released into an animal sanctuary. That's the first piece that we're going to work with. Now you might just say, oh, hey, doesn't that just imply that C is 40? Well, careful. We just need to check and make sure that at T equals 0, our population is 40, okay? So we're just going to, in fact, let's break this up. We're just going to say find C. I just wouldn't jump to that conclusion just yet. We proved it for the simpler kind of exponential growth, but we don't know that yet. All right, so we know that at time 0, my population must be 40. Okay, so let's say 40 equals, all right, well, let's see. We have L over, well, we know what L is. We know that L is 4,000. That was given. So then 1 plus C e to the, well, T is 0. So everything up here is just going to go to 0. All right, and then that gives us 40 equals 4,000 over, well, e to the 0 is 1, so we just have 1 plus C. All right, and then we just do a little bit of algebra. All right, if you cross multiply and solve for C, you should find that C is actually going to be 99. Okay, so that gives us our constant for C, which was not the value for the initial population. All right, so just look alive there. The second thing that we will have to do is find K, right? C and K are parameters of the equation that we will need in order to be able to make predictions with that equation. All right, so that's our next goal. We're going to find K. All right, and we're probably going to do that using this second bit of information here, right? After 5 years, the elk population is at 104. That'll probably be helpful. So basically, right, at T equals 5, we know that Y is 104. Hooray! So we can say that 104 must equal, again, we still know that L is 4,000, 1 plus, now we know C is 99, e to the negative kt, and we know that T is 5, so I'm going to say to the negative 5k. All right, and so then this becomes a bunch of algebra, all right, and right, you're just going to cross multiply. You're going to solve for k. It's in an exponent, so you will end up having to use natural logs, all right, and I am going to assume that you could do that now. I'm not going to step you through every little bit of solving, but you should be able to get to k is about 0.194, all right, which would give us our completed formula. That's a 3, right? We would be able to write y equals 4,000, that's L, 1 plus 99, that's C, e to the negative 0.194 t. Great, that's our completed formula. All right, and so now we've got something to work with to actually answer the question that we were given. Predict the population after 15 years. So that just means we're going to let t go to 15. So basically y of 15, right, will be 4,000 over 1 plus 99 e to the negative 0.194 times 15. And all I'm going to say is just be careful in your calculator. This is an opportunity where there are just multiple ways to make a mistake in your calculator. So just be careful. And if you've done all of that correctly, you should get about 625.67. I'm going to say you can round either way, but I'm going to say we are not at 626 whole elk. So I'm going to call that 625 elk. And that's enough of that. Again, I've skipped a lot of steps, but a lot of the steps that I've skipped are pre-calculus steps. So please do go through them, make sure you can do them, and let me know if you'd like any help working through those intermediate steps. And that's it for exponential growth and logistic growth. Don't forget to check out the graphs just to see how they look and how the carrying capacity is shown in those graphs.